right, hello. So we're going to continue here in Chapter 12 on simple machines. Now, up to now, everything we've talked about is a variation on levers. So we talked about levers, we talked about wheel and axle, and we talked about pulleys. So now we're going to go on and talk about the next type of simple machine called an inclined plane. And so we're starting at the bottom of page 255, and it covers through page 257, even on to the next page, 258. Okay. So what I've recreated up here, you should be now on page 256. So there's a figure 12.12, and I have this shown up here. So let's talk through let's define our terms for an inclined plane and see what kind of equations we're going to use to solve inclined plane problems. So we have this inclined plane. Now, why would you use an inclined plane? The typical classic example is that you use this. Sometimes an inclined plane might be called, a lot of times it's referred to as a ramp. So you might have some kind of object or box or crate, and you're pushing it up an inclined plane because you want to get it up to some platform or lever or platform or level platform or the back of a truck or something like that. All right, so we have our plane at some angle. There's some object that we're pushing or pulling up the inclined plane using some input force. This object has some weight to it. Now we're going to consider whatever's happening along the plane, we're going to consider that as where the input is happening. Because remember, with simple machines, we're trying to distinguish between input and output. Now, with an inclined plane, it's not quite as obvious, but this is just the way we're defining our terms. Is the output is defined as, for instance, if you had decided, well, I'm not going to use a ramp, I'm just going to take this object, this is the same object as this, I'm just going to take this object and I'm just going to use brute force and I'm just going to pick this up and I'm going to set it up here wherever it is I want it to be in the end. So the output is considered to be, if you did just that, if you pick this up, your output force is equal to the weight of the object, and you're lifting it up some height. So this dimension is lowercase h, that's considered the height of the inclined plane. Now there's one more dimension. On the input along the ramp, we have a dimension, and we'll use the lowercase s to be the length along the ramp itself. So we have, and this would be considered, if we want to think of input and output distances, you could think of this as the input distance, and you could think of the height, if you wanted to, as sort of like the output distance, if we want to be consistent with the other equations we've used in the past. But as you can see from the text, we'll just use S and H. Okay. So the first thing we're going to do is just just quickly develop the equation we're going to use for ideal mechanical advantage. So if we assume there's no friction loss, and of course that's just an assumption which in reality is not true for an inclined plane, but if no friction loss, then we have work input equals work output, no friction loss. Now remember, the equation for work is equal to force times distance. So on the input, that's input force times the distance, which along the ramp is S. Output work is equal to the weight of the object times the height that you're lifting it. But as in many of the problems we've been working, the weight and the output force is the same. In other words, the output force you're exerting is equal to the output force that you're accomplishing is the same as the weight of the object. So we'll just change that in this equation to output force. All right, so now I'm going to do a manipulation. I'll just use algebra to manipulate this equation. So I'll just recreate it here. Input force times S equals output force times H. I'm going to divide both sides by H and both sides by input force. So if I divide both sides by H and both sides by input force, then this equation manipulates into this form. Now you recognize this. This is actual mechanical advantage, which, remember, no friction loss, that's the same as ideal. So here we go. If this equals this equals this equals this, do you buy this then? There is our ideal mechanical advantage equation for an inclined plane. So the ideal mechanical advantage is equal to the distance along the plane, S, divided by the height of the plane. And as we said a minute ago, this makes sense because we're considering this lowercase s to be the input distance and the height to be the output distance. So remember, with previous simple machines, we've used input distance over output distance for our ideal. And this also follows what we've done before, where ideal mechanical advantage is based on dimensions or distances, where actual mechanical advantage is based on actual forces. All right, so let's look at an example problem. I'm just gonna. This is not one that's in the textbook. So just use this same sketch, and let's say we have a distance along the plane of 5.4 meters, and let's say we have a height of 1.6 meters. And then let's also say the weight of the object is equal to 420 newtons. So the first question that you could be asked, let me give myself a little bit more room here. The first question you could be asked is, what is the ideal mechanical advantage of this inclined plane? So as we just saw, S over H, which is the 5.4 meters divided by 1.6 meters, so that would be 3.4. Again, the mechanical advantage is a unitless number, the units cancel out. So there's your mechanical advantage. And another question you might be asked is, if the input force is equal to 175 newtons, in other words, if it takes a force of 175 newtons to push this object up the ramp, then what is your actual mechanical advantage, which is based on forces? So you remember that actual mechanical advantage is force out over force in. Force out is the same as the weight of the object, so that would be the 420 newtons that you were given, divided by the input force of 175 newtons, and if you divide that out, you get 2.4. So your ideal, which assumes no friction loss, gives you a mechanical advantage of 3.4. Your actual mechanical advantage based on real forces is 2.4, which is not unusual for an inclined plane. There's a lot of friction loss. So now the next question is, here's another question you might be asked. Part C to this problem is how much work was lost to friction? So, same equation we used before. So, friction loss equals work in minus work out. So work in along the input of the inclined plane is input force times the distance along the plane, and the output side is equal to the weight of the object you're moving times the height of the inclined plane. And remember, the work, or the weight of the object is the same as your output force. So let's continue this up here. So your friction loss then is equal to your work in, which is the input force, which we were told a minute ago, which is 175 newtons, times distance along the plane, 5.4 meters, minus your output work, which is the weight of the object. What did I tell you that was? 420 newtons times the height of the plane, which is 1.6 meters. So then, if you do the calculation, your friction loss then is equal to 945 minus 672, and you can see the units are Newton meters. And you also, from our previous discussions, know that Newton meter is the same as a joule. So you could answer it in Newton meters or in joules. So you subtract that out, that ends up being your friction loss is 273, and I'll just abbreviate it J for joules. And one last question, that was part C. Here's part D, is what is the efficiency of this inclined plane? Now you remember that we had three different equations that we could use for efficiency. Okay. One was work in over work out over work in. In other words, what's the comparison between how much you get out compared to how much you put in? And so that would be your output work, which is the 672 joules divided by your input, which was 945. If you would like to express it in percent, you could multiply by 100%, and that should give you 71%. And there's another equation you could use in this case. Remember, we tacked on a third equation for efficiency, which is actual mechanical advantage divided by ideal mechanical advantage. So you remember from earlier, at the beginning of the problem, we determined that the actual mechanical advantage is 2.4 and the ideal was 3.4. Multiply that by 100% and that should be the same. There's some rounding going on here, so it's not going to be exactly the same, but if there wasn't rounding going on, then they would give you the same numbers. So if you were doing a practice problem or a graded homework problem or a test problem, you could see that either one of those equations would work for you, and I would accept either solution. All right, one last problem to go over. I want to go over this example 12.5, which takes up most of page 257 and also goes on over to page 258. Now there are a number of errors in this example. So let's take a look at this. All right, now this is a little bit different way of looking at an inclined plane problem than the one I just went over. So again, 12.5, I've recreated this sketch that's at the bottom, page 257. Now I'm also using a little bit different terminology. You'll notice that they're assuming that this crate is being pushed up the ramp. So they've used the letter capital P for input force. I'm just using input force as F with a subscript I, just like we have, just so we don't confuse matters. Okay. So a crate is being pushed up, and you notice we're doing a free body diagram, so we're getting back to chapter 4 stuff. So we have this ramp. Now you're also given that the height is 2 meters and the length along the ramp is 4. So the first thing you see happening in here, if you're given those dimensions, then you use trigonometry to figure out what the angle of the ramp is. So the angle of the ramp, I've already written in 30 degrees here, but just as a refresher, so the angle of the ramp is the inverse sine of h over s, or the inverse sine of 2 over 4, and that ends up being 30 degrees. So this just, you can see at the top, there's just a little bit of trigonometry there just first to figure that out. All right, so let's go with it. So we have a 30-degree ramp, and we've taken the x and y axes and we've tilted the x and y axis so that x is along the ramp and then y is perpendicular to the ramp. So you have a number of forces here. You have the input force either pushing or pulling this object up the ramp. You again have a normal force, the ramp pushing back on the crate. You have the weight of the object straight down and then resolved into its x and y components. And this is a case where the object is being pushed up the ramp and it's in motion. So the friction force that's opposing motion is kinetic friction. And we already have our table built, so we can fill in our table to help solve this problem. So this problem is asking you for two answers. One is ideal mechanical advantage, which is the easier one, since we have dimensions, and then actual mechanical advantage, which will be a little more difficult because what we'll have to do is a solution for the input force. We already know the output force because it's the weight of the crate. All right, so part A, we'll dispose of that pretty quickly. Ideal mechanical advantage is input distance over output, which we know for a ramp is S over H. So it's the 4 meters over the 2 meters, or 2. So ideal, assuming no friction loss, you get an ideal mechanical advantage of 2. Okay. All right, now we have to solve for input force. Well, first off, we can, part B is what is actual mechanical advantage. So that's force out over force in. Force out is the weight of the crate. That's given to you as 88 kilograms. And then you would just multiply by 9.8 meters per second squared to convert that into newtons. And that ended up being 862.4 newtons. I'm not sure that's actually spelled out anywhere as that number, but you can see the effort to multiply 88 times 9.8. So that is our output force. So now we need the input. So let's fill in our table. So for the normal force, none of it's in the x direction, all of it's in the y direction. The input force, all of it is in the x direction, none of it is in the y direction. The kinetic friction force, all of it is in the negative x direction, and none of it is in the y direction. And for the weight, so for the weight, we can do a little calculation here. 30 degrees. And we've already figured out our weight is 862.4 newtons. So your weight in the x direction would be the 862.4 times the sine of 30 degrees. And you can see that in the middle of page 257. And the weight in the y direction is the 862.4 times the cosine of 30 degrees. Both of these are negative because weight in the x direction is in the negative x direction, and weight in the y direction is again in the negative direction. Now the other thing we can do to move this table along is we can come up with an expression for the kinetic friction force. So you remember that kinetic friction force is equal to the kinetic coefficient times the normal force. You'll see early in the problem we're told, in the very first paragraph at the top of the problem, we're told that the kinetic friction coefficient is 0.3. So this ends up being 0.3 times the normal force. And this is in a again, still in the negative x direction. So there we go. So we can set each of these columns equal to 0 since we're in an equilibrium situation. We have motion, but we don't have acceleration, so we're going to consider this equilibrium. So the normal force is equal to 862.4 times the cosine of 30 degrees. And that, if if you do the calculation, that ends up being 747 newtons. So we can solve that right away. And then it's going to be handy because we're going to do a substitution over here. So now we'll add up this column, set it equal to 0. Input force minus 0.3 times the normal force minus 862.4 times sine of 30 degrees is equal to 0. We're going to take our normal force from the other column, plug it into here. And now you see that we have only one unknown. We already know the normal force, so the input force is the only unknown left in that equation. It turns out, I'll speed this up here, it turns out if we solve that equation for input force, it ends up being 655 newtons. Now this is where there's a typographical error. If you look at the very bottom of page 257, just above the figure, they've got this same equation we have up here, but they say it's equal to 755. That's a typographical error. It should be 655 newtons for the, they call it P, we call it input force. Then on the top of the next page, then they go on to do a calculation of actual mechanical advantage. And again, you'll see that the 755 was erroneously continued on that top of page 258. So it should be, the denominator should be 655, not 755. And then the actual mechanical advantage then is the 862.4, which was our weight, divided by the 655. So our actual mechanical advantage ends up being 1.32. Okay? So you can see how the problem can become more of an equilibrium type problem with trigonometry, or the other kind could be like the one I showed you before. Okay, what I would say now, your homework then would be to go on and tackle practice worksheet number 2 in the workbook. And that is, let's find it in the workbook. Alright, let's hold on here a little bit. Worksheet number 2, it starts on page 106. Okay, so work that. There should be answers in the back. And then come in tomorrow with any questions you might have. All right, that's it.